Good morning, folks. This is Todd Coburn of Cal Poly Pomona with the Aerospace Structure Series. This morning we're going to be covering Lecture 17a of the content that corresponds with Aero 3261. We're going to be studying especially shear and thin-walled open sections. Now we saw in our last lecture how to calculate shear. Back in Lecture 3, we learned about shear stresses P over A when we have a stubby thin section where the parabolic distribution of stress doesn't change much. We can approximate the shear stress as P over A. We found out last lecture that shear stress distribution is actually parabolic, and it's governed by the equation VQ over IT. Now today, while that works, that VQ over IT is the correct formula for what we're going to cover today as well as last time. But last time we moved from top to bottom of the section, looking at a single parabolic distribution like that. When the cross-section is thin, made of thin flanged members like an I section or a J section, what happens is the same formula governs VQ over IT. However, now, instead of just moving from top to bottom, we're going to find out we get a distribution of stress that varies throughout the section. We're going to have to work from the extreme flanges of the fiber. So if we have say a C channel, we'll work from the extreme edge where the shear stress has got to be 0. We'll see how the shear stress builds up within the member as the Q increases, right? As we get more and more area, the area times the Y minus Y bar is the first moment of the area Q. So as we move away from that point of 0 stress, we're going to get more and more Q, which means we have more and more shear flow, which means we have more and more shear stress. We'll find that the shear stress builds up, and then starts to diminish. Remember, everything above on one side of the neutral axis will have a positive Q. Everything on the other side will have a negative Q. So the summation of all of them is 0. That's how we found the centroid of the section, by finding out that point where the Q above and below is exactly 0. So we're going to find out as we move from an extreme fiber, our Q builds up until we hit the centroid, and then it diminishes because we're going to be subtracting out that extra Q. And this change in Q, first moment of the area, is directly proportional to the shear flow in the section and the shear stress in the section, where the shear flow is VQ over I and the shear stress is VQ over IT. Now, in the last section, since we're moving from top to bottom, our T, or our width dimension, or thickness, was actually the width dimension. But now when we're working with thin flanged open sections, the value we need is a value as we're moving doing our shear flow calculation, moving toward the centroid, moving along the center of these little flanges. You take a look at the direction of the shear flow, and actually our T dimension in the VQ over IT is the width or thickness of the member perpendicular to the path of the shear flow. That's what we're going to be using. So it'll again be VQ over I and VQ over IT, but then our little T dimension is changing the way it's defined slightly. Okay. Once again, this is very common in aerospace. It's a very important thing to learn because all of our sections, most of our sections, are rather thin. Now, the reason we're calling this thin shear and thin-walled open sections is because if the section is open like a bunch of flanged elements, like an I section or a C section, then this applies. If actually it's a closed section, it's actually a little different. We're going to find out next lecture that it actually is the shear flow in the member. The shear flow through the member, if it's rather thin enclosed, the shear flow will be constant unless we hit another web where the shear flow can go off to, branch off to, and the shear flow in the member will be proportional to the enclosed area of that. We'll learn about that next time, okay? But right now we're going to be learning about shear flow in thin-walled open sections, looking at further applications of our equations VQ over I and VQ over IT for shear flow and shear stress. Let's see how it works. Enjoy. Last time we looked at the shear flow and the shear stress in a section, and we covered sections. Basically, we didn't really differentiate what kind of section we were evaluating. But what we did for a shear acting downward, let's say on the part, like this, we looked at the shear flow that we get, how the shear flow changes
as we move from top to bottom, whether we had a rectangular solid member or a thin-walled member, we basically just evaluated the shear flow moving downward through the section. What that means is we calculated the shear flow, say for this section, we can look at the shear flow here, 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 or here. And to do that, to calculate the shear flow here, we find what is the Q away from the CG from this point. We draw a line through this point. Is there any area above here away from the CG? No. Therefore, our shear flow, VQ over I, is 0 at that point because our Q is 0 at that point. If we had done the next point, we would have found this point, drawn this line, we would have taken the shear flow of that, which is V this Q, which means this area times this Y bar is our Q. If we had picked the next point, we would have seen from down here at the centroid, that means everything away from the centroid. You can actually take either the top or the bottom, and your value will be the same because the CG is defined to be the point where the Q is the same above and below that centroidal axis. Therefore, regardless of which Q you use, you will get the exact same shear flow by definition. The only difference is, in the one case, the upper piece you're going to get one shear flow, and in the other piece you'll get another shear flow. What that means is, if you look at your member like this, it's now cut in half, and here's the bottom half. If we had used this Q, let's say we have shear that's acting downward, what that means is the shear along this surface is acting in the same direction. This shear is also acting downward, which means this shear is moving the opposite direction. So you'll see these shears, these two shears are equal and opposite. These two shears are in the same direction because our little romantic shear flows have to be mouth to mouth and tail to tail. So by using the upper Q, you're going to get this shear flow. By using the lower Q, you'll get that other shear flow. If we had taken a point below the neutral axis, like this point, we would once again cut off the area away from the CG. This is the CG. Now we have two choices. We can use this Q or the Q down here in our VQ over IT equation. If we had used the upper Q, we would have had this much positive Q where the Y bar is positive and this much negative Q where the Y bar is negative, and that would give us the exact same Q as if we had just used this Q, which just gives us this negative Q, the area of this times its Y bar, which happens to be negative. So no matter how we cut it, as long as we do it properly, we will get the same value. In the same manner, if we had analyzed this I section, let's say we wanted the shear flow here, we would have just cut off the piece, and we just took this Q to get our shear VQ over IT. If we had wanted the shear flow at the middle, we would have then taken the Q here. Now, this is how we did it last time, moving from top to bottom. Top to bottom. And this is how we get the shear flow. One way to get the shear flow when we're just concerned with horizontal changes, which is valid mostly for stubby sections, not as much for thin sections. Now we can still use the same approach, like to get the shear flow at this point right here. We can use either what we did last lecture or what we're going to do this lecture to calculate that shear flow. But if we wanted to calculate the shear flow here, for instance, the method of going from top to bottom would have given us a value, but the more critical value will be if we use what we're going to learn today, which basically means we're going to move differently. Let's take a look at that. So what we're going to cover today, rather than move from top to bottom, is we're going to move from the outer extremities toward the CG. And this will work for any thin-walled section. For example, if we look at the CG of these parts, outer extremity means moving from the CG through the part, we're going to move to the furthest points. That means this point, or this point, or this point, or this point, this point, or this point. If you take a path from the CG of these sections, that's as far away as you can possibly get. So what we're going to do now, instead of taking horizontal slices, we're going to take slices that are perpendicular to the segment that we're working on. So we can calculate the shear flow at this point, 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 this point, this point, this point, this point, stuff like that. So what we're going to do now is we're going to be cutting off at the point. So that means we're cutting off everything here. The Q of that, for that point, the Q will be this area times its Y bar to get our, if we wanted the shear flow here, we would have cut off, moving from the extremities, we would have found all this gets cut off. So this will give us the same answer as we had using the other method, top to bottom, and so will this point here. But when we're in these horizontal flanges, then it changes. So we want the shear flow here, we'll cut this off and get the area times the Y minus Y bar of that. Another example. If we want the shear flow here, we would just take that Q, that area, times its Y minus Y bar. If we wanted the shear flow here, we would get that area and that area times its Y minus Y bar, and so on. If we had flanges like this and wanted the shear flow here, we do the same. See how that works? Okay, let's go ahead and derive those equations working through our lecture. The first one is going to show you how to do this with calculus, and you're going to find that that probably is a little challenging to absorb. If you want further reading on that, I recommend that you read E.F. Brune's corresponding sections. Okay, let's consider a beam. Now if you look at this beam, what we're really seeing here is this is just a simply supported beam. Look, we've got a simply supported beam, which means we have a reaction here and a reaction here, and normally we would just see that as a little beam like this with a point force here. That's really what we're looking at, and because this is a big deep I section beam, it's shown as deep as it actually is. But this is really just a simply supported beam with a load, a transverse load on the span. What we're going to do, so there's our cross section, and what we're going to do is focus on this little segment here, and we're going to draw a free body diagram as shown here. Now, since this beam has both shear and moment on it, this little free body diagram does not show the shears, but it does show the normal stress. We see we're going to get a normal stress distribution on each face of the cut, DD prime and FF prime, as shown. It's going to be tension and compression depending on where the CG of the part is. And the neutral axis will be at the CG as well, which is what's shown in the picture. Now, what we're going to do, if we focus on this lower piece and make a section cut there, we've got part of the distribution of stress. Once more, our shear stress is not shown, at least not the vertical shear stress what we have is just the normal stresses. We see we've got some segment of those normal stresses. And just due to those normal stresses alone, we see that we're going to need more reactions. We're going to look at that in a second. We can remember that our stress at any point is my minus y bar over I. And recall that we can write the stress anywhere in the cross section as a function of its relative distance. Remember that y, that distance from the CG to the point, that y minus y bar, that's what we're seeing here. We can write the stress at any point is a function of the maximum stress times the position of the point where you want the stress divided by the total max distance from the centroid. So since we call that max distance C for mc over I, we can say that it's just the max stress, or in this case the tension stress, the max tension stress, times the y, the position where we want the stress, divided by the C, or the max position for that segment. Okay, with that, and remembering that our bending is just mc over I, which means we can write that same stress as that stress over C times the YDA, which is our Q. We can calculate the total load on the face, which is simply that relation. It's just summing up all of the stresses and their little corresponding elements of area. That's the total load on area CD, and then the total load on the cut at FE. Now, recalling that the stress is just mc over I, we can plug that in. We can write our loading, our total force on CD with that relation, and on FE with that relation. Now, if the beam has a constant I, if it doesn't, it's going to get more complicated. We're going to ignore that potential for now. We can write the total horizontal, the difference in force between face CD and face EF, as the difference in moment, m minus m prime over I, times that integral YDA, which is just our Q. Now, if we sum our forces in the positive x direction like this, we're going to find that those forces plus that shear force, if you see I popped a little red shear arrow here on the face that we cut, that force times its area, which is B dx, we can solve that to get the shear stress. And we find that the shear stress is just the change in the moment divided by I, and the width, and the dx times the Q. Recalling that the change in moment with respect to x is just the shear, we can plug that in and write that the shear stress is just V over I and the width times the integral of YDA, VQ over I width. This is exactly the same equation that we saw last time. And we can use this equation to calculate the shear stresses or the shear flows through calculus. This equation shows the shear stress, and to get the shear flow, what would we do to this equation? That's right, we would just remove the B. VQ over I is the shear flow, VQ over I width dimension at the point is the shear stress. Got it? Now, if we look at this more closely now, using that same relation, we can work our way through the beam. Once again, we're going to work from the extremities. Since this is a thin section, we're going to move from the extremities towards the centroid. And we're going to focus on using that equation as we do that. Now, we can actually do this kind of philosophically using good engineering judgment quite simply. Or we can use calculus to solve for all the shear flows. If we use calculus, we're going to have to pay very close attention to our sign convention. Our sign convention will change the results that we have. So here's our sign convention. You can see we're going to say X is positive to the right, Y is positive going into the page. You'll notice this beam has a P on the back end, and we've got shear flows on the near end. What this means is we have a cantilever beam. Now normally most books will show beams that are held on the left and cantilever to the right, or held back in the page and coming out of the page they become free. This particular one through Brune is done backwards, where you can imagine you're holding the beam with your left hand close to your face, and then you're putting a force on the beam with your finger down in the page where P is, which means basically it's a cantilever beam where the reaction is coming toward you. The beauty of this nomenclature is it allows us to look at the reactions of the beam rather than equivalent forces on the beam. So we can see the applied load P, and we can see that all the shear flows that we're getting are in the reactionary shear flows, and are in the opposite direction. Okay, so we're going to focus on one little element, that little element in the corner. Let's pull it over here. You see on the right we've got that free face. The top and bottom are free faces, and the left side at point B is where we've cut the segment. So our distribution of stress is causing, if we've got a positive bending moment, it looks like this force is going to give us compression on the top. So you can see moving into the page, you can see we've got a compressive force on the back side, Cy, and a compressive force on the front side, Cy prime. Now these are actually stresses. There's stresses on that segment, and the stress times a little increment of area, which is dx, times T will be the force. And what we're showing here are the forces. Now, if you look at that force acting back, stick your finger back out there in the page and push up, you see that that force is giving you compression, true, and is that causing the moment to increase as it comes toward you or to decrease? You can see it's increasing, the moment is increasing as it comes toward you. That means Cy prime is larger than Cy. Now it's not critical to understand this, because if you get this direction wrong, then you will calculate a negative shear flow from what you assumed. But if you get the direction right, then your shear flow calculation will come out positive, confirming that you did it correct. So let's take a look at this segment again. We've got Cy on the back end. We've got Cy prime on the near end. And then we've got a cut segment at B where we've got the dy dimension. You'll notice we have a little shear flow, Qy, acting back toward the back of the thing. So it's acting in the direction of the positive y-axis. Now we assume that for two reasons. One, because that's the positive y-axis. And two, because we suspect that that's the correct direction. Now we're going to sum our forces in the y direction, and that means we're going to have a Cy, a negative Cy, plus a positive Cy prime, plus that little shear flow times that little increment dy. You see that? We're going to do that in a minute. So we're going to go ahead and sum our forces in the positive y. They must be equal to 0. That means we have that little shear flow Q times dy. Since Q is a running load or a shear flow, we have to multiply by the distance to get a force, plus Cy prime, which acts in the same direction, minus Cy. That must be equal to 0. We can solve that for the shear flow, which says the change in the force divided by dy is equal to the shear flow, and it says in the negative direction of that change in force. Now we know that that change in force, the force on each is just my over I times the Q, and the Q is just that integral, the summation of the little z dA's. In this particular case it's z, because z is the up dimension, right, as we're moving from top to bottom or from right to left. So the z dA, which is the Q, times that change. So we can plug that in, and we can say, well, the shear flow on that face at cut at B is just the negative of dm dy, 1 over I about the x-axis, and that integral of the Q. Recalling that the change in moment with respect to y is just a shear, we can write it this way. Once again, this is just VQ over I in disguise. So let's redraw that segment that we just calculated a moment ago. And let's now start from a different corner. Let's start from the corner over on the other edge, and we see the same thing. We're going to get, so this is the upper left corner. We see we're going to have a C prime and a C, and we're going to have this little shear flow dy times qy along the edge that we cut. Now we see that the shear flow on the left edge has to be 0, as the shear flow on the right edge of our prior cut had to be 0 because it's a free edge. What that means is our shear flow is increasing. Let's take a moment to think about that. Let's go back to the first one, and we look and say, look, the shear flow here has to be 0. Why? Because if we make a cut moving from the centroid toward the outer surface, there's nothing out here, which means the area out here is 0. That means the Q is 0, which means our shear flow is 0. If we had taken a cut right here, we make this cut, now we have a little bit of area. We have an area and we have a Y bar. If we had made a cut here, then it's actually this area times its Y bar. In the same manner, when we look at this little piece here, we can say the shear flow here is 0 because moving away from the centroid is 0. Because remember, this is just one piece of our beam, which is not all completely shown here, right? So the shear flow here has to be 0, but the shear flow here will be some value because now we have an area and we have a Y minus Y bar. Does that make sense? It is critical that you understand this concept at this point, lest everything we do be wasted. Okay. With that said, we're now ready to look at the lower corner down at D, and we see now what we've got is a little tension force, one on the back face and a tension prime on the front face. Once again, our cut face has a shear flow, but now, because the tension is greater near us, the shear flow better be acting in the other direction as shown there. If we jump over to the lower right, our E, we can draw our little element and we find the same story. And if we draw the top, everything, the entire upper cap, we get this figure going from 0 at each extreme fiber to some value down below. If we draw the lower piece, we get this. And we can systematically solve our beam by applying this formula. The shear flow is just the negative of the shear over I and integrating up the ZDA. If we study this a little further, we look at this beam with this element. Now if we wanted the shear flow at point A, that A prime B, what we would do is we would focus on the piece that has been cut away, which means we would focus, if we wanted the shear flow at this point here, we would just cut this part away. We would take the CG, we would get the distance to the centroid. This is our Y minus Y bar. Our area is just this area. So our Q is just this area times this Y bar. And then that means the shear flow here is just V, that Q over I. And we see, because the shear is acting downward here, what that means is we're going to get shear is going along this face here. It's coming here. If we redraw this element, we can see that if this is a positive, this looks like a positive shear, which means it's generated from a positive moment, which is giving us compression on the element, which is building up as it comes toward us, which means we're just going to have a little element of P here and a little P plus delta P here. We can simplify this by ignoring whatever the actual force is, just look at the change in force, and we can see our shear flow is going to be acting like this direction. which means it's acting in this direction, because remember, head to head, tail to tail. Now what that means is, because our area out here is 0 and our area here is something and over here is something more, as we move this way we're getting more and more area. That means our shear flow is going from 0 at this point to a larger and larger value as we move this way and get more area. That's why we can have a 0 shear flow on this face. Now the shear element would have to look like this, but over here the shear is 0, over here the shear is something. It's increasing as we move this way. Since our shear flow along this face is acting this direction, the shear flow on this face must be acting this direction, and we can see, and that will define all the shear flow directions for our beam. What this means is, if we had started over here and done the same thing, we would have had another little segment. Now once again, we find out we're going to have a slightly larger force here, delta P, and that's going to be resisted by the shear flow here, Q. Now since these are romantic, if the face of the mouth of this shear flow is that direction, that means these better be in that direction, going from 0 at this face to some value over here, to a larger and larger value as we move this way. Okay? Now you'll see when we come together, now that means as we start going down, we're going to have shear flows going like this, coming with shear flows coming like this, which means we're going to have even more shear flow. Whatever the shear flow is in this piece, plus whatever the shear flow is in this piece, is going to be what shear flow here. It's kind of like a faucet. If we plug in a faucet on this end, and plug a faucet on this end, and then turn on the water, all that water is going to be coming like this. Whatever accrues here is going to go this way, whatever accrues here is going to go this way. Think of the shear flow with that kind of idea. So once again, if we cut an element from the upper piece like this, we can see the directions here. Shear flow on the upper edge, then at any point we can calculate this shear flow is equal to VQ over I. If we want the shear stress at any point, we're going to just take the shear flow over the thickness. What does that mean? That means if we want the shear flow, if we calculate the shear flow here, it's VQ over I, and if we want the shear stress, we're going to divide by the thickness there. Now if we had been working from top to bottom, we could have done this to get the shear flow there. If we work from side to side, then we're going to work like this to get that. Which one do you think is going to give us a larger shear stress? This cut with a big wide B value of that dimension, or this guy? Right? So when we have a stubby section, it's acceptable to just move from top to bottom. But when we have a thin-walled section, we're going to move from extremity toward the centroid, extremity toward the centroid, and beyond. Okay? And when we know the shear flow at any point, we will get the shear stress by dividing by the T, 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 whatever the thickness is at that point. Which is why we often say that the shear stress is VQ over IT. It's actually that T is the width dimension, and if we're moving from top to bottom, it's the horizontal width. If we're moving through the member, the thin members, it'll be perpendicular to the thin dimension. Make sense? It does make sense. What you need to do is wrap your mind around it until it makes sense to you. Now we could write that this way, because that shear stress is on the Z face acting in the X direction. The shear stress is on the Z face. This is a Z face, right? Here's Z, and that's perpendicular to that face. And the shear flow is acting in the positive X direction. So using our tensor nomenclature, that shear stress to be properly identified is the shear stress on the Z face in the X direction. We learned about this nomenclature from our first couple lectures onward, and that's how it works. ¿Te gusta? Nishiwanma. Great. Now, once again, we can look and say, well, any little element, you can see now our element, our shear element, which we often draw like this, is now lying horizontally like this. If we get a shear flow going like this, that means it's going to be like this and like this and like this. Now, if we have a nice constant segment, or if our piece is small enough, all these shear flows will be the same. Certainly these flows are the same here, they're the same here, but remember, this flow is increasing from here to here as we get more and more area moving from here to here. Therefore, the shear flow along here is not constant, it's growing. The shear flow here, which is defined by whatever area is out there, whatever transverse area is out there, which is zero. The shear flow here, because now we got this area as we move toward the centroid, that's not zero, and it's getting larger and larger as we move this way. That's why our shear flow is building from 0 to some value, and it's always going to be matched by the same value going into the page. Okay, I think we've said that about 4 different times the same way. Focusing on this little element here, is what that means is we've got this little guy and this little guy. We said this is a Z face and the force is in the X direction. This is an X face and it's in the Z direction. Therefore, our shear stress on the Z face in the X direction is equal to our shear stress on the X face in the Z direction. Now remember, before we move from top to bottom, if we had done that, we would have been moving from up here down toward the CG in this direction. And if we look at a little element, what that means is if we look at a little increment of piece like this, we would get a little force, a little shear force. Let's draw a little element. This is a little through the half thickness here. What this means is we would get shear stresses going like this. That means we have shear stresses going like this and coming out of the page like this. So if we look at our little element, let's look at this on edge. That means this is giving this, which is giving this, which is giving this. Now, because this is super thin, we know this has to be 0, the shear stress, and this would be our shear stress on the X face in the Y direction. Actually, that one's in the negative Y, right? Now, that shear stress in the X face in the Y direction is the same as our shear stress on the Y face in the X direction. That's the little guy up here. That's the little guy right on down here. Now, if you look at our little flange, we know up here the shear stress must be 0 because there's no area away from it. And down here the shear stress is 0 because if we draw a cut here, that point right here has got to be 0 also. That doesn't leave a lot of room for the shear flow to develop between the thickness. So when we had a stubby section, it was okay to do all these horizontal slices and move this way. When we have a thin section like this one, we can't, because out here this doesn't make sense because we have 0 here, 0 here, and everything in between is thin. Therefore, the shear flow that makes sense is moving from the extremity toward the centroid. So that's why we're making cuts going this way rather than this way. Okay? That's what this says over here. The shear stress, this vertical component of shear stress, once again drawing that little flange, we saw before this component is significant, but this component here is negligible because this must be 0 and this must be 0, and this doesn't have a lot of distance to build up. So basically this is negligible. This shear flow is dominant for thin-walled pieces, and this shear stress is negligible. That's why we're saying here that those stresses are 0. Got that? And then this is just saying that the shear stress out here and here and here and here better also be 0. Okay. With that said, I believe we are ready to move on. If we have shear on a section, vertical shear, that gives us vertical shear, but what gives us horizontal shears in the section as we make section cuts is when our bending moment changes. The shear due to that bending moment that changes. Remember, shear in a beam, when the shear is in the beam, the moment will change. When the moment changes, we are going to get different forces, normal forces, from one segment to the next. And when the moment changes and the shear changes, the normal forces change, that means we're going to develop shear flows. So this is just showing a simple free body diagram. This is showing a little element at B and the forces on that cause the shear flows on that, and element at C, and how that shear flow moves from extremity toward the centroid. So first it's moving inward and then it's moving downward. Now it's like we're filling up and then dumping out. So what that means is the shear flow is building. Now remember, the Q is increasing. Q is increasing as we move from here to here, from here to here, and from here to here. But then because our Y is negative, we're going to get that, whatever the Q is right at this point for everything above it, if we move right down here, we're going to get that whole Q plus some negative, plus more negative, plus more negative. When we get back out to here, we're going to have removed all the Q that we had for the upper section is all going to be gone. That's why our shear flow is building as we move this way, building as we move this way, building as we move this way. Then it's diminishing, diminishing, diminishing. Got that? So we can kind of see that also. If we look at this point, there's no area this way, therefore the shear flow here is 0. The shear flow here is 0, the shear flow here is 0, and the shear flow here is 0. That means we're going to be moving, as we move from these extreme fibers inward, the shear is increasing along here, right? Increasing. Increasing until we get to here, to this point right there. And if we move from this 0, we're going to find the shear flow increases till we get to this point. If we start at this, we're going to see that shear is 0 here and it's increasing, and 0 here and it's increasing. Now we're just looking at the magnitude here. We're not looking at the relative directions. This flow is showing the relative directions. We know the shear flow better be moving this way and this way to feed this. Now once we get to here, we've got whatever the shear flow was coming from over here, whatever the shear flow was coming from over here. If we call that Q, that means the shear flow right down here as we start down into this leg is going to be 2Q. Because we have a Q from the one side and a Q from the other side, like two hoses feeding it. So we know the shear flow here is 0. The shear flow here is VQ over I, where Q is the area and the Y bar. You'll notice, so we get a shear value here and a shear value here. Now, how does this change? As we move from point, we'll call this point A, to point B, we'll notice that the V doesn't change and the I doesn't change. V and I are constants of the entire section. We're looking at V on the whole section, and we're looking at I of the whole section. What's changing is the Q, the area and the Y bar. Now if we look at this little piece here, we see as we move this way, we see that the thickness is not changing. The area is increasing, so as we move from there to there, we can say the little increment, the little ds, the little increment of length is changing as we move this way. And we see that the y minus y bar, that's just this distance from here to here. That's the y we see there. That's not changing. So this t is a constant and this y is a constant. and this ds, only this dimension is getting larger. So that means we're getting a linear increase from here to here. It's a linear increase. A linear increase. You see that? And if we work from this edge, we know this is 0, and we're going to get a linear increase to there. We have a Q over here and a Q over here. That gives us our 2Q. Now when we start moving downward, you'll notice we have all of the Q of this segment, and now we're going to get a little more as we move down. At each point, if we look at this point, this point, this point, we'd have these little areas. So we'd have, we'll call this Q of the flange. Then we're going to have this little increment of Q, this little increment of Q, and this little increment of Q. So at this point right here, we're going to have this Q plus this Q. At this point, we're going to have this Q, we're going to have those summation of those 3 Qs, and so on. Now you'll notice as we move this way, what we're going to do is have a certain Q value for this flange, plus we're going to have a thickness, and we're going to have a little ds component. So as we move this way, we're going to get more and more ds, and our y is changing. Our y is actually decreasing as we move this way, right? Because we're getting closer to the centroid. So what we see is, moving from over here, we have a certain shear flow, but our Q is increasing as we move this way, but it's increasing by less and less and less as we move closer to the centroid. What that does is means we are getting an increase, but it's a diminishing increase, so we're getting a decaying function here. You see that? Because it's a function of our ds and our y and our thickness. That is constant. This is increasing linearly, and this is decreasing. The decrease is making this increase in length of less and less effect, which is giving us a first order decay, which gives us this shape, which I'm exaggerating here. Now once we pass the CG, we're then going to be adding some negative Q, which means we're then going to decay until we get to this value. You'll notice this value, since it's fed in the same manner, of course the directions are opposite. This is also 2Q, since these Q's are the same Q's as we had above if this is actually a symmetric section. We look here and we see that the shear flow is 0. We look here and we can calculate the area and the y of that, and we can calculate the shear flow at this point. We can see that it's linearly increasing. This is symmetric about this axis, so this is doing exactly the same thing. So if we calculate that 1Q, that we've got both of those Q's, that means we've also got this 2Q at this point. Then we come down to here and we say, okay, now we can take this Q and add it to this Q, the Q we already had. So we already had calculated one of these Q's. We'll call this Q flange 1, and this Q of flange 2 is going to be identical. This Q of the upper web is going to be the area and the y minus y bar of that. So when we want to calculate the shear flow at this point, we'll call it the CG. We take the summation of this, this, and this. All 3 of those Q's are what feed that in our VQ over I relation. So we really only did 2 calculations, right? We calculated 3 Q's. We calculate 3 Q's. Only calculated 2 Q's. We calculate a Q for one little segment here. And we know this Q is the same. We calculated a Q right here. So we took 2 of these Q's. We calculate this. Then we multiply it by 2. Then we calculate this Q. We'll call that Q3. Add those together, 2 Q's and a Q3. Add them together, not divide like it looks like I'm doing. We calculate the shear flow based on this first Q and the shear flow based on this third Q. That gives us this flow and this flow. And this flow. We know this one's increasing linearly and this one's increasing like this. Let's draw this one more time. So we calculated, call this QF1, and we calculated this QWeb1. Our shear flow at point, we'll call this point B. We'll call this point B, and we'll call this C. So at point B, it's going to be V Q flange 1 over I. We know the distribution is linear from here to that Q. This is QB. And this is also QB changing linearly. Because this is symmetric about this axis, these are both 0, and these Q's are also QB changing linearly. And as we move to here, now we calculate, this next thing we're going to calculate, we calculated our QW1, so our Q at the CG is going to be V over I, and now we've got Q, our total Q is going to be Q of web 1 plus 2Q of the flange 1, because there are 2 of those feeding it. That gives us the shear flow right here. Since our force is acting downward, our shear force, the equivalent shear flows better be downward on this face. And that means these better be feeding it. That's going to give us all of our directions, and these are going to be bleeding it. You can say everything above the neutral axis or the centroidal axis is feeding it, because we have a positive y, and everything below is bleeding it because we have a negative y. Now that doesn't mean that the shear flow is always above the centroidal axis will be downward. That's a function of our loading. In this particular case, our applied load here is down. Our equivalent shear flows better be down. But we're going to have a feeding and a bleeding going on. Okay, now we know, we calculated this point, and now that means this QCG, that's the value here. We know this is 2Q as we move down into here. This is the first point down in this web, and then this is going to be increasing. It's not linear, it's actually going a little faster than linear, but slowing down as it approaches the CG. And then as we bleed, it's going to be diminishing by the same amount. This is 2Q. So we would identify the magnitude of 2QF, and this is QF, and this is QF1, right? And this is this. We would identify this, draw this picture. If we wanted to show how this should look, what we would do is calculate QF1, QWeb1. We would then take 2 of these and 1 of these to get QCG. Then we plug this guy into our formula to get Q1, plug this guy into our formula to get Q3. We're going to take twice Q1 to get Q2. So what this means is, and now that we have this, we can draw everything. We know the magnitude here, 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 and here is 0. Right? Pounds per inch. The Q here is Q1 pounds per inch, right? And we know it's increasing linearly, and it's in this direction. This one's going to be in this direction, and it's increasing linearly to the same value. We now have 2Q1. We write that magnitude here. We're going to draw what this distribution looks like. We're going to write QCG at this point right here, and we know we're going to be something increasing faster than, but getting slower and slower increases as we move toward the CG, and then it's going to be bleeding it by the same manner. Once again, this is 2Q1, and we draw the direction of these where we're feeding and now bleeding. That's, when you're all done, you should box this kind of answer. You've got the shear flow identified at each of the points 1, 2, 3, 4, 5, 6. Let me do that again. 1, 2, 3, 4, 5, 6. Magnitude down here. 7, 8, 9. And all of the corresponding arrows. That's how we solve this. That's how we report our answers. If we look at this guy, we're going to see the same thing. Let's do some annotations here. Now, the easiest way to solve this guy is to start with our section and say, well, we're going to need the shear flow here. So let's just go ahead, and since this is symmetric, let's take this Q. That Q is going to give us, in our VQ over I, is going to give us a shear flow. We'll call that the shear flow at point, let's call this point A. Okay? That's going to give us a shear flow at A. Now, if we come down here to the CG, we're going to now add the Q of these two guys to get a QCG, which means we're going to take this first Q plus these two Q's. That will give us the shear flow at the CG. Now, we know that the shear flow here, this shear flow, actually this VQ over I, actually that's the total shear flow, but look, we have two paths. Only half of it comes to each of these, so that means we're going to divide this guy, this first one, by 2. This means the shear flow here is this magnitude, and the shear flow here is that magnitude. Now, if we make a section cut like right here, let's take a section cut right through the middle here. If we make a section cut right here, right there, how much area do we have away from the centroid? Remember, we had to come this way to get to that point. Is there anything beyond this point? No, therefore the area here is 0. Right here, the area away from the centroid is 0 due to symmetry. What that means is this is increasing from 0 to this value we just calculated, from 0 to this value. And whatever we calculate here and here is the same as here. This is also QA, and this is QA. Then what happens? Now as we move downward, once again, we can calculate this Q at the centroid. We know what that is. And once again, since we're moving this direction, we're getting a function which is not linear. It's something faster than linear, but slowing down, and then it's bleeding in the same fashion. And then due to symmetry, we can see it's like this. Okay? Let me draw that again. Here's our segment. We calculate the Q of this piece, and then the Q of this piece, and show what it is. We know it's going from 0 to that value, from 0 to that value. We see this is the same Q, and this is the same Q. Remember, this is if we use the Q of the upper piece, this whole piece, then this would be VQ upper over 2I. If we had used the Q of 1/2 of this, let's say that's Q of half the upper piece, then Q would have been VQ of half the upper piece over I. See the difference? One used half the Q to feed it, the other one used the whole Q. The one that uses the whole Q has two paths to get out of there. Either way, you'll get the same value here. This is the same value here. Then we get the Q of the upper web, and we say, well, the Q at the CG is going to be the Q of the upper web plus Q upper, or 2Q half the upper, right? The total Q upper plus that Q of the upper. Oh, we've got two of these Q's of the upper web too, the way we defined it too, right? We got one over here and one over here. So we got 2 of those upper web Q's plus the Q of the upper. That gives us Q at the CG. We can use that to calculate the Q of the CG equals BQ over I. That gives us this value. This is not increasing linearly, it's increasing something faster than linear that slows down and then bleeds off. So we calculate, we show our Q here, we show our Q here, going to 0, show our Q here, show our Q here, and our Q there. Then we show our directions, which means we show these little directions, like, actually I'm going to draw it over here. We show our directions like this. They're all feeding, 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 and bleeding. See that? That's how we're going to do this. Box that mother. That's what this says. Once again, we saw this problem solving the same way. Let's go ahead and practice again. What would be a correct solution for this? We would draw our section. We would show the shear flow here is 0 and it's going to some value. We'd calculate that Q. We'd show that these guys are going this way. Then we're going to say, okay, this is 2Q. We're showing the magnitude of that. 2Q, that's the magnitude of that. Now we only have one web, so we only draw one picture. If we had two webs, we'd draw two pictures. We've got the Q at the CG, and this is increasing like this, increasing like that. And that means we're going this way, this way. This is Q again. And then we show our areas. These are all going down. These are bleeding it out. Now, we'd show the magnitude of this, magnitude of this, magnitude of this, magnitude of this, magnitude of this. Q equals 0 over here, Q equals 0 over here, Q equals 0 over here, Q equals 0 over here. We'd use proper sig figs and appropriate units and show the directions of those shear flows. This would be the way you would report your answers for this kind of problem. If I ask you to draw the section, that's what I'm looking for too. So we can practice this. Actually, as you get better at this, you can say, well, are we looking for reaction or equivalent shear flows? Often for these we're going to be showing equivalent. If we're looking for the equivalent shear flows, you can see if the shear is acting in this direction, then the shear flows on this face better be acting the same direction. And anything away from the centroid this way better be feeding it, which means the shear flows are coming toward it. And anything below the CG better be bleeding it, which means they're moving away. Right? See how that works? You can do the same thing by taking a little segment. We take a little piece here, that little piece, right, making this little cut. You see, well, where I cut it is this face here, which means I'm getting a shear flow like this. For positive bending, we're going to get a little more compression over here, which means the shear flow is going to be resisting that. That means if that head is coming this way, this head is coming that way. That tells us what this direction is. We did it philosophically in the upper picture, and now we're doing it analytically. In the same way, if we took a little more, like we turn the corner, whatever was happening here, it's going to be the same thing, and then that's going to be corresponding with a shear flow like this. If we took that whole upper piece, moving down into here, what we'd see is these guys are coming like this, and it's starting to go down, which means this guy down here is coming out of the page like that, and so on. That corresponds with this picture here. In the same way, we can see if this is our applied shear force, these better be acting in the same direction. Anything above the CG is feeding, anything below is bleeding. And for this guy, these guys' equivalent shear flows better be in the same direction, and then we bleed that mother off. In the same way, these better be in the same direction. And usually to show that they're shear flows, instead of drawing a big arrow like this, like I just did, we'd show little arrows like was already shown to show it's a shear flow. That makes it a little clearer. It's not a force, it's a flow. Here's a little sample problem. Calculating the shear flow here at A and the shear flow here at C. There's the Q. There's the shear stress. Once again, the shear stress is just VQ over I times the appropriate width dimension, which in this case is the thickness. Now, the easy way to do these is to do what we just did and just to kind of walk ourselves through. So remember, if we look at our I-beam, now if we want to know, we're also going to want to be able to turn these into forces. Once we have identified all of our shear flows, we'll call this Q1. And our directions, right? Okay. Once we've done this kind of thing, we're also going to need to be able to calculate what forces correspond. Now, we know that the shear flow here is 0 and the shear flow here is Q1. So what is the force from here, from A to B? Well, it would be the integration of this shear flow across this distance. Now, if the shear flow were constant across that, like if we had a shear flow, if the shear flow had been constant across this upper flange, Q, then that shear flow times this distance, QDS, would be our force. But in this case, our shear flow is going from 0 to some value. Therefore, all we need to do is calculate the area under that. That Q1 times that little ds, we can call that, let's call that the B of the flange, right? Times B of the flange. That's the distance, but actually only half of that, the area under that is just 1/2 because that's a triangular distribution. So our force in the upper flange, the upper right flange, is going to be 1/2 Q1BF. See that? If we want to know how much force is in this one, well, it's by the same amount, by symmetry, 1/2 QBF. How much force is in this vertical web? Well, it's the summing up these guys, which means the force due to all this, that's part 1 of the web force, is going to be 2Q1 times the height of the web. And force in the other part, this little piece here, we'll call it 2 web, is going to be QCG minus Q1, right? Or minus 2Q1, right? That difference from here to here. And then what we need is the area of that. So that's the magnitude of that. We can say, oh, that is a Audi kind of increase. So it's this guy. So it's 2/3 BH times 2/3 B, the distance that it's traveling, is going to be in the total web, this whole length. That will be whatever the height of the web is. So 2/3 BH, right? And that gives us the force. So the total force in the web would be the summation of these two guys. You can calculate the force in the web above and below the neutral axis, centroidal axis, or you can calculate the total force in the web like we just did. So we're going to need to not only be able to calculate our shear flows like we did, but be able to calculate what is the force in each flange. And these two relations make it really easy. We can evaluate our Q's is just by evaluating the area and the y, and this is actually y minus y bar, right, of the section. and we're going to calculate forces by evaluating the area under those shear flows and how it develops. Okay, so these two relations make that work a little easier. That's all I got for you. Enjoy.